Welcome back to our next chapter, chapter 5. We're going to be looking at integrals, which we saw at the very end of chapter 4, but we're going to be really expanding on that, getting into some meaning, getting into how we find these integrals and stuff like that. This section is on area. We're actually not going to be using any calculus in this section. We're going to be using geometry. And basically, the idea of what we're going to do is we're going to be finding the area underneath curves, or we're going to be approximating the area underneath curves, rather. And we do that by making a bunch of rectangles or trapezoids, kind of like you see in the picture here in the background. And then we can use that to approximate the area underneath the curve. And so when we're doing this, there are a few different types of ways we can draw these rectangles or trapezoids. The first way is we can use what are called left sums. And in this case, we're going to draw a bunch of rectangles where the left-hand side goes up to the function, and then the right-hand side doesn't necessarily go up to the function. So here, if we're finding the area underneath this curve from 0 to 10, we can draw a bunch of rectangles. Start there, the left-hand side goes up to the function, then it goes over, comes down. The left-hand sides of the function, over and down. The left-hand sides of the function, over and down. Over and down, and then over and down. So here we have a bunch of not very well drawn rectangles, but you won't actually have to be drawing the rectangles, which is nice. But we have a whole bunch of rectangles. To find the area of the rectangle, it's just the base times the height. So it would be this distance times whatever this distance is, plus this distance times whatever this distance is, plus, and then we keep it up for all of them. And so that's a left sum. The next one is a right sum. You can be doing the same thing, except instead of going up on the left-hand side to get to the function, you go up on the right-hand side to get to the function. So here, our first rectangle, you'd be up there, over and down, up there and over, up there and over, up there and over, up there and over. So, and then the area, again, it's the same. It's the width times the height, but in this case, this would be the height, plus the width times the height, plus width times the height, plus width times the height, etc., etc. Now notice in the left-hand one, in this case, since this is a pretty much decreasing function, the left one gave us a whole bunch of extra area here. So this is going to be an overestimate. The right one, we had a bunch of missing area. So that's going to end up being an underestimate. If it was increasing, that would be switched around. But since it's decreasing, that's the way it goes. There's two more ways of making rectangles we don't really talk about, but there's the lower rectangles and the upper sum rectangles. The lower one, you would always just choose the ones that would give you an underestimate. So like the right sum in this case is a lower sum. And then the left sum would be an upper sum because you always choose the one that gives you an upper estimate. Not horribly useful, but what those do is it actually gives us a bounds. We give a lower bound and upper bound, and we know that the actual area is going to be in between them. But again, we don't actually use those much, so we're not talking about those. Another way of approximating rectangles is to use the midpoint of the rectangle as your height. And so in this case, instead of going up on either side, we would go up in the middle of the rectangle to the function. The rectangle goes each way. We go up in the middle, rectangle goes each way. Go up in the middle, rectangle goes each way. Go up in the middle, rectangle goes each way. And so what this does is it generally will give us a better estimate because each rectangle is going to have some underestimate and some overestimate. Some underestimate, some overestimate. And so that helps counter out these big areas of either all underestimate or all overestimate. So again, the midpoint generally gives us a better approximation. We do have to find more values usually in that case. But that's one way of doing it. And then the final way of approximating area is not using rectangles at all, but rather using trapezoids. So we have trapezoidal sums, where here instead of going straight over, we're going to use both endpoints are going to be on the function. And we can make a trapezoid. And then both endpoints are on the function. And we can make a trapezoid. Both endpoints, we can make a trapezoid. Both endpoints, trapezoid, and we'll just go straight to the end here. Both endpoints, trapezoids. And you might be thinking, that doesn't look like a trapezoid. I remember trapezoids looking like this. Well, if you remember what a trapezoid is, has one set of parallel sides, which in this case would be those, and then one set of non-parallel sides. Well, our trapezoids, the parallel sides are actually the vertical ones. So these trapezoids are just on the side. I'd say you could rotate your phone, because I know that's what you're watching this on, 90 degrees, except the auto rotate doesn't make that work out so well. But that's the trapezoids. So when we have the area formula for a trapezoid, which is 1/2 base 1 plus base 2 times height, or base 1 plus base 2 times height divided by 2, the bases are the y values. The height is actually the width of the rectangles. So it would be the change of x. So in our case, this usually looks like the base 1 plus base 2 is going to be a y1 plus y2. The height, that's the width, is going to be an x minus x. If we're looking from A to B, that'll be B minus A over 2. And we'll see this, we'll actually see one on the next slide. So finding trapezoids, notice that gives us a really good estimate. Most of the time, a trapezoidal estimate will give us a really good estimate. So what kind do you use? Whatever it tells you to. It will tell you exactly what kind of sum to use. Sometimes it'll say use left sum and a right sum. That means you're doing the problem twice, once with left, once with right. So the first step is finding areas using tables. And this is actually a really important topic because it gets to the concept of what it is that we're doing. In the next section, we'll learn how to use calculus to do this from an equation, which is how you'll do most of these area problems. However, the concept part is important. So on the AP test, they like to test that. This is the way they can do it because you can't use calculus to do this if you're given a table. So we're going to look at our table, which has these values, and we're going to find a couple different sums. We'll start out by finding the left sum. And so for the left sum, and for actually all these sums, our widths we look at the intervals. We're going to have 4 subintervals, 0 to 2, 2 to 5, 5 to 6, and 6 to 9. For the left sum, we'll use the height of 4 because that's on the left for the first one, and then 3, then 2, then 4, and we won't use that last number. So for the left sum, the area is going to be we're going to have 4 times the width is not an x value, it's the difference of x values. 2 minus 0 plus, the next one is 3 times 5 minus 2 plus, the next one is 2 times 6 minus 5 plus, the next one is 4 times 9 minus 6. And so we can do the addition subtraction first. So we'll have 4 times 2 plus 3 times 3 plus 2 times 1 plus 4 times 3. And now you can do the calculations. We'll have 8 plus 9 plus 2 plus 12 is going to be 31. 8 plus 12 is 20, plus 9 plus 2 is 31. So the left area is 31. Next, we'll look at the right area. And so over here, instead of starting out with the 4, we'll start out by using the 3, and then we'll use the 2, 4, and 6. So in this case, we'll use that last one, but we won't use the first one. The intervals, the x intervals, stay exactly the same. So if we're looking at this, we'd have the area is going to be we're going to have 3 times 2 minus 0 plus 2 times 5 minus 2 plus 4 times 6 minus 5 plus 6 times 9 minus 6. Work on simplifying again. So we'll have 3 times 2 plus 2 times 3 plus 4 times 1 plus 6 times 3. Which means this approximation of the area, we're going to have 6 plus 6 is 12 plus 4 is 16 plus another 12 plus another 18, sorry, not 12. 16 plus 18 is 34. So we have one area approximation is 31. The next one's 34. The next one, we won't have 4 subintervals for the midpoint because we need more values. For the midpoint, one interval is going to be from 0 to 5, and the other one is going to be from 5 to 9, because we have to know that value in the middle. Now, granted, these aren't actually midpoints of this, just because this is the table we're using, but it'll be close enough for what we're doing. So, how to do this? It's going to be basically the same. We won't need quite as much room because we only have 2 intervals, but the area, the height, is going to be 3, and the intervals from 0 to 5. So we're going to have 3 times 5 minus 0 plus, this one's going to be 4 from 5 to 9. So 4 times 9 minus 5. So that'll give us 3 times 5 plus 4 times 4. 3 times 5 is 15. 4 times 4 is 16. So in this case, the area is going to be about 31. And then finally, we can use the trapezoid rule. So the trapezoid rule, area is going to equal 1/2 times, we're going to add the two y values together, 4 plus 3, times 2 minus 0, plus 1/2, 3 plus 2, times 5 minus 2. So we add the y values, we subtract the x values, plus 1/2, 4 plus 2, times 6 minus 5, plus 1/2, 4 plus 6, times 9 minus 6. Simplify. Right. 1/2, 4 plus 3 is 7, times 2, plus 1/2 of times 5, times 3, plus 1/2, 6 times 1, plus 1/2, 10 times 3. Couple of things you could do here. You could factor out the 1/2. You could just multiply straight through. We'll just multiply straight through. So our area is going to be approximately 1/2 times 7 times 2 is 7, plus 1/2 times 15 is going to be 15 halves, or 7.5, plus 1/2 times 6 times 1 is 3, plus 1/2 times 10 times 3, that's 5 times 3 is 15. I have no idea where that red line came from. Anyway, add these together. You have 10 plus 15 is 25, plus 7.5 is going to be 32 and 1/2. And so that would be using the trapezoid sum. We can find that. That's tables. With equations, as you can see from the slide, the first step is to find the values, then put them into a table, and then it's the same thing. So if we're going to approximate the area of fx equals x squared from 0 to 10 using 2 intervals, 5 intervals, or 10 intervals, this is how we're going to do it. So using 2 intervals, first you have to figure out what the intervals are. We're going from 0 to 10, so the width, it's going to be 10 minus 0 divided by how many intervals? 2. So here the width is going to be 5. So we can make our table from 0 to 5 and from 5 to 10. Those would be our 2 intervals. We're using the left-hand rule. So in this case, the area is going to be approximately 0 times 5 minus 0 plus 25 times 10 minus 5. Notice the widths will always be 5 in this case. The widths are always 5. The next one, the widths will always be a different number. So we don't actually have to do the subtraction, we just put in 5. And in fact, we could actually factor out that 5 and then just add those y values together. In this case, it doesn't make that much of a difference. 25 times 5, the area is going to be about 125. But as we have more intervals, factoring out that number can be very handy. So the second one, we can see the interval width is 2, and that's because 10 minus 0 divided by 5 is going to be 2. So this width is always going to be 2. And then we'll find the left sum. In the next one, 10 minus 0 over 10 is 1, and so the width is always going to be 1. We can make our table. It's just a good way of organizing your information, and that way you're always working from the same thing. There's less chance of making mistakes that way. So here the area is going to be 2 times 0 plus 2 times 4 plus 2 times 16. I'm going to factor out the 2. So I have 2, and then it was times 0 plus times 4 plus times 16 plus times 36 plus 64. And remember, with left hand, we don't use that last one. We can add together the inside there. 64 and 36 is 100, plus another 20. So we're going to have 2 times 120, which is about 240. That's a big difference from our first one. We'll see why in just a second. The last one, we have 10 subintervals. And so we have to find all the values from 0 to 10. The width is 1, so we can factor that out. We'll have 1 times 0 plus 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49 plus 64 plus 81. We can add all these guys together to get 285, if I'm not mistaken. Times 1 is just 285. And so that's another change. And so here we can find it with as many subintervals as we want. It's just the more subintervals we have, the more difficult, maybe not difficult, the more annoying it becomes because there's just a lot more going on. But all we're doing is multiplying to find the areas of rectangles and adding them together. And so what happens when we get more subintervals is our area disappears. So this is from that last problem. With 2 subintervals, we had the one with area 0 and the one with area 125. But look at all of this space that was missed. With 5 subintervals, there was less space that was missed. We still have an underestimate, but it's closer. With 10 intervals, there's even less space that's missed, but there is space. So the more subintervals you have, the better your estimate's going to be. And so to make a really good estimate, we use a lot of subintervals, and that's where we will continue with next time. So today you are finding areas of rectangles and trapezoids and adding them together. It's just geometry. So keep working problems, keep asking questions, and until then, happy mathing.